So we saw how to do a problem with osmosis. This is the next slide. So osmosis is important in many biological processes. You already know this. You've already taken anatomy and physiology. You know that solutions are moving across semi-permeable membranes. And so if you put a cell into an aqueous environment, water is going to move back and forth. But if it turns out that the water and there's not equal solute concentrations on both sides of the cell membrane, more water can move in and out, and you can end up with a cell shrinking or a cell exploding. And so here's a nice, happy little red cell. You notice a little dimple in here that's placed in an isoosmotic solution. It's isoosmotic or isotonic solution. Isoosmotic is another way to say it. An isotonic solution. Iso meaning the same across. So the solute particles on this side of the cell are the same as on the other side of the cell. In case of blood, that's about 300.3, somewhere around 0.3 osmolar on both sides of this membrane. So water's moving in at the same rate as water's moving out. If I put this blood cell into a hypertonic solution, meaning that it's going to be greater than 0.30 osmolar on the outside, where on the inside it was 0.3 osmolar initially, what's going to happen is that water is going to leave this cell. And as it leaves the cell shrinks. If you place it into a hypotonic solution, in that case what you have is you have less than 0.3 osmolar on the outside, and it's 0.3 osmolar on the inside. In this case, because it's more dilute on the outside than on the inside, water flows in. You can see this red cell is starting to expand, and it will expand to the point where it breaks. All right, so now we've seen an example of this with cells. I'm going to show you another problem here. We've looked at one thing that happens in the hospital is we have saline solution, physiologic saline solution. And we saw that it has 0.304 osmolar, so it's close to the osmolarity of blood. Now what I'd like you to do is I'm going to have you pause here and try to calculate the osmolarity of a 5% glucose solution. Actually, it turns out in the hospital that glucose is referred to as dextrose. So try to compute the osmolarity of a 5% weight per volume dextrose or glucose solution, and the AMU, so it's 180.2 AMU. So I'm pausing now, we're waiting. All right. I'm over here now because you turned it off and then I ran to the other side, and now you're ready to see how to work the problem. So I hope you really paused it because you need to try to do these without me showing you how. So we first know that we're going to take the glucose, C6H12O6, and if we throw glucose into water, C6H12O6 aqueous, and so since glucose doesn't break apart, I is equal to 1. Actually, since I have the board here, I can draw what glucose is, so it looks like it's a hexose, meaning a 6-carbon sugar. So that's what glucose looks like. And you can see all of the hydroxyl groups that are on here. All of those can form hydrogen bonds. That's why it dissolves readily. Okay, now we come over here. So we saw that I is equal to 1. The osmolarity is equal to 1 times the molar concentration. So we need to calculate that from the 5%. So moles per liter is what we need to find. And so we know it's 5 grams of glucose, C6H12O6, in 100 milliliters. milliliters. Converting it to liters, 1,000 milliliters is 1 liter. And then we know that it's 180.2 grams of glucose per 1 mole of glucose. So grams cross out, milliliters crossed out. I'm left with moles per liter. And if I put this into a calculator, I come out with 0.277 mole per liter. And it's maybe not as high as you expected. This is an estimate of the value. All of these are estimates. So it's about 0.3 osmolar. And so if I put the 0.277 in here, you see that it's 0.277 osmolar solution. And so it's comparable. All right, so we're going to stop the video at this time, then we're going to begin on the next one with looking at another colligative property.